So thank you for introducing me, and thank you very much for inviting me to give this seminar. The today's talk is prospects of heavy dark Z at multi-TeV muon colliders. I'm from Konkuk University, and the talk is based on my recent paper, which is done with my postdoc supervisor, Professor Jong Hyang Song, and Professor King Man Chung, and Jinung Kim and Sujin Lee are the students of Professor Song. Okay, so let me start. And this is the outline of my talk. So first I will discuss why we need an additional U1 gauge boson, which is a dark gauge boson, commonly referred to as a dark photon A prime or the dark gauge boson ZD. So I will use these two terms interchangeably. So both are equivalent. And then I will discuss the existing constraints and the projected sensitivities from the current experiments and future experiments in the dark Z parameter space. Then I will talk about the motivations of going into muon collider as a future collider experiment. And then I will talk about the search prospects of heavy dark Z at muon collider via the annihilation channel, where the dark Z is produced in association with the ordinary photon. Okay, so the question is why we need an additional dark gauge boson. The very simple answer is that it can be used as a portal, so which connects the hidden sector to the visible sector. So this is the schematic representation of the dark sector paradigm. So on the left-hand side, we have the ordinary matter, and on the right-hand side, we have the dark sector candidates. And they can interact or talk to each other through this portal called the dark photon or the dark gauge boson. And also the dark matter particles within the hidden sector can also interact with each other, just like the ordinary matter interact with each other through the electromagnetic force. Okay, so the dark gauge boson, ZD, that mediates this force can obtain a small coupling to the electromagnetic current due to the kinetic mixing between the standard model hypercharge and the dark U1 symmetry. So this operator is given by this, where the F prime mu nu is the field strength tensor of the U1D symmetry, and B mu nu is the field strength tensor of the hypercharge symmetry. And this epsilon is a small kinetic mixing parameter. So the dark Z obtains a mass mZd via the dark Higgs or the Stackelberg mechanism. So we do not need to go into the details of how the mass is generated. So in the minimal dark Z model, we have three unknown parameters. One is the mass of the dark Z and the kinetic mixing parameter epsilon. And the other one is the dark Z branching ratio to the hidden sector, which is either 1 when kinematically allowed, or it is 0 if it is kinematically forbidden. Okay, so we can have two basic scenarios. When the dark matter is heavier than the dark Z, which is called the secluded dark matter scenario. In this scenario, the dark matter freeze out is obtained by the annihilation to the pairs of on-shell dark Z by this process, followed by the dark Z decay into the standard model particles. So in this scenario, we do not have any thermal targets because the annihilation cross-section is independent of the epsilon parameter. So in this scenario, the dark Z is restricted to decay only into the visible sector because the dark Z is the lightest in the hidden sector. And another scenario is that the dark matter candidate is lighter than the dark Z. In such scenario, the dark matter annihilation is given by the S-channel process, and away from the resonance, the annihilation cross-section is proportional to this quantity. Here alpha D is the hidden sector fine structure constant. So in this scenario, we can have a thermal target, which is large epsilon and small dark Z mass. And in this scenario, if this dark Z to decay to the dark matter is open, then the decay is almost by 100%. Okay, so So what are the production modes of this dark Z in the accelerators? So I have listed the four main dominant production modes. One is the Bremsstrahlung, where an incident electron or a proton beam radiates dark gauge boson during an interaction with a fixed nuclear target of charge Z. So over here, Z is nothing, no, it's not the Z boson, it's just the charge of the target. Another one is the annihilation channel, where the electrons or positrons can collide and produce a dark photon or dark Z in association with dark photon. This is the conventional search strategies done in the lepton colliders. And then comes the Drellian process, which is a QQ bar annihilating to dark Z. And this is the standard search strategy in the hadron colliders like LHC. And the last one is the meson decays, where the neutral mesons like the pion can decay into dark Z in association with a photon. And
Excuse me, in the channel 3, you said that the annihilation of ZD is 100% to the dark matter.
This one, second scenario.
No, the third, in the third case, the Drellian case,
Drellian case.
ZD decays to what?
Conventionally, in hadron colliders, it's the ZD decays into the leptonic channel, because if you go to the hadronic mode, then the background will be very large. So the leptonic decay of dark Z is considered.
Yeah, but this is model dependent. So ZD is because ZD is mixed with the standard.
ZD is yes, it's mixed
Yeah,
with the
okay,
standard
okay.
photon
Okay.
because of the kinetic mixing
Yeah,
parameter.
okay.
Yeah. So finally, I also talked about the pion decays of dark Z and normal photon. So on the right hand side, we have the Feynman diagrams for all the production channels of dark Z. Okay, so let me now go into the decays, and based on the decays of this dark Z, we have to make the strategies to look for it in the experiments. So in the visible, if I talk about the visible decays of dark Z, then we can have either the prompt decays or the non-prompt decays. So when the epsilon is large or dark Z mass is large, then the decays are mostly prompt. So in the prompt scenario, the decays of the vortex of the dark Z decay and the production of the dark Z cannot be distinguished. Whereas for the non-prompt or the displaced decay, the vortex from where the dark Z is decaying and the production of dark Z can be distinguished properly. So for that, for the non-prompt decays, we require very small epsilon or very small mass of the dark Z. Next, we can have the invisible decays of dark Z when the mass of the dark matter is very low compared to the dark Z. Such strategies look for events with an imbalance of energy and momentum, because the dark matter which were coming from the dark Z just leave the experiment detector without any trace. And the third strategy is to search for the rare interactions of the dark matter particles in a detector placed downstream of the ZD decay point. So it's kind of like a direct detection of the dark matter in the accelerators. Okay. So if there is any question, then kindly let me know. Okay, these are the current constraints from the experiments and the projected sensitivities in the for the visibly decaying dark Z. So on the first figure shows the current constraints from the electron beam dump experiments, which are shown by the red regions. The proton beam dump experiments are shown in this light blue region, and the electron colliders going through this green distributions, and the electron on fixed target experiments through these yellow regions. So these regions are excluded by the experimental searches done so far. And the LHCb can also probe this non-prompt decay mode, and they have done this kind of exclusion over here. This is epsilon less than 10 to the power minus 3. So this region is the prompt decay modes of dark C or the dark photon, and these regions are the non-prompt decay modes. So the non-prompt decay modes can be explored in beam dump experiments only, and in colliders like LHC or like the electron positron collider, they usually look for the prompt decay modes. Only LHCb has the sensitivity uh, to uh, to figure out the displaced vortex, and that's why they have these kind of exclusions for small epsilon. Okay, so in the lower panel, we have the proposed future sensitivities with the same color scheme as above. So for the electron collider, we have shown the exclusions coming from the Bell 2 experiment, and the LHC probe, the sensitivity of LHCb is shown over here for the non-prompt decay modes, and this for the prompt decay mode. And for the phasor, the sensitivity is given like this. And this is the future sensitivity for the dark quest. This is the proton beam dump experiment. Okay, so these plots are taken from this reference. This is a nice review on the dark photon at accelerator. Okay, now let's talk about the invisibly decaying dark Z. So in that case, on the upper plot, upper figure, we have the constraint and the proposed sensitivity from the electron colliders given in the green shaded region, and the electron beam dump through this red region, and the meson decays in this purple region. And the projected sensitivity coming from the Bell 2 is also given over here, this green line. And the Na64, the projected sensitivity for Na64, which is like a electron beam dump experiment. The projected sensitivity is given over here. And this is the thermal targets for the scalar and Majorana and zero Dirac dark matters, with alpha D given like this, and the mass ratio is given like this. So we can see that the current experiments have already excluded a large portion of the thermal targets.
Excuse me, can you remind us what is alpha D?
Sorry, I cannot hear you properly. Can you
Can you remind us what is alpha D?
Alpha D is like the U1 gauge coupling, just like the fine structure constant in the hidden sector. I mean, the dark matter candidates interacts with the dark Z through this alpha D.
Okay, so the real so the coupling to the standard model particles is through the product of alpha times alpha D or something like that?
Yes, because through alpha D, I mean, since the standard model particles are not charged under the U1D symmetry,
Right.
so
So there is epsilon here.
yeah, so
So
that's why
epsilon.
we have the epsilon over the kinetic mixing parameter. But
Okay.
this alpha D is nothing but the U1D
Okay. Epsilon alpha D. Okay.
U1D charge, yeah. And this is the constraints on the invisible for the invisible decaying scenario on the dark matter mass and the Y plane. The Y was given over here like this candidate. Okay, so this is a constraint on the M chi versus Y plane for the searches of ZD produced. For searches for ZD produced in proton beam dumps with subsequent scattering of chi particles detected downstream are shown over here in this blue region. Yeah. And these are the Babar and the LEP experiments from the E plus E minus collider as given over here. And this is the thermal targets. So as we can see, the projected, I mean, the current exclusions and the projected sensitivity can really rule out the thermal targets, and this shaded gray region is actually the direct detection constraints on the scalar dark matter.
Sorry, when you say thermal target, you mean the parameter space that corresponds to the correct relic abundance? What is?
Yes. So along this line, we can have the correct relic abundance, and above this, the relic abundance is, the relic abundance is just below the observed relic density.
So the relic abundance is correct. So is the red line?
Red line over here.
Which is the line, the thermal line?
Thermal lines, these are the black lines.
The black line.
Yeah, given like this, yeah.
Okay. What is the red line instead?
Red line is the projected sensitivity from the NS64 experiment. It's the electron beam dump experiment. So electron beam is targeted on a fixed target, and the dark photon or dark Z, they are radiatively produced through Bremsstrahlung, basically. And those dark Z decays into the dark matter. So in the upper figure, in those kind of experiments, what they do, they get an estimate of the dark matter. The events they collect should have a large imbalance in the momentum and energy. Where in the second experiments which I'm talking about, like the LSND or mini boon experiments, what happens? The proton beam dump experiment are used. So proton beam is fired on the targets, and the dark photon which is radiatively produced, they decay into the dark matter, and those dark matter basically recoil from electron or nucleons, just like the ordinary direct detection experiments. So it's like kind of a direct detection searches in accelerator in these experiments.
In this case, but the dark matter particle is in the dark center, so you are free to set up how it interacts either with electrons or with the nucleons. It's kind of free, right? So
Once the dark matter is produced from the decays of dark photon, so dark matter basically recoils from the electron or nucleon through this dark Z.
It's always through the dark because it's a portal. So in other words, all the cross sections are fixed once you fix alpha D and
once you fix alpha D, so epsilon, and for in this kind over here in this figure, epsilon and the dark photon mass are the independent parameters. But over these experiments, so the mass of the dark matter is also important. So I have taken the ratio to be like 3. The dark photon mass and dark matter mass ratio to be 3. The smaller the dark photon mass is, the better is, the larger is the thermal cross section. So if you see this scattering cross section, annihilation cross section, then you can see that when the dark Z mass or the dark photon mass is smaller, then sigma V increases. So I have taken some kind of a pessimistic scenario where the ratio is 3, almost close to the resonance.
And you should have also some indirect detection, maybe some annihilation rate to
Indirect detection.
No, what I mean is if you have annihilation, can you show you have annihilation of dark matter particles to visible particles, to standard model particles? Can you go back to the previous transparency or previous? Sorry, here.
It's okay.
Chi Z star FF bar. So you should have some signal from the galaxy or from annihilation of dark matter particles, right?
Yeah, but the dark matter is lighter than the yours. But yeah, I understand what you're asking, whether the current indirect detection
Yeah,
constraints.
yeah. So I'm just
Yeah,
asking if there exists also limit for this
yeah,
kind
of course, there should be a limit. I mean, in this reference, they have only shown the
of.
constraint from the direct detection. In fact, the direct detection limits are much more stronger than the indirect detection.
Uh-huh.
So maybe that's the reason.
I
Also, you
see.
can see
Okay.
that for the scalars, this region has been this
Mm.
shaded region, the gray region, is for the scalar dark matter, and it actually rules out the dark matter candidate.
Yeah, depending on the type of if you have a scalar dark matter, probably this is P wave and you have no signal.
Yeah,
But if you have a fermion dark matter, Majorana dark matter is pseudoscalar, so the Z boson, so then it's S wave. You should have a signal. You know, it depends on, so in other words, depending on whether the dark matter is scalar or a Majorana or a pseudo Dirac, you should have also an indirect detection signal that, however, if it's in P wave, of course, is suppressed. You don't see
yeah.
it in the case of a scalar. But probably in the case of Majorana, you may have also some signal. Okay,
I
thanks.
mean that will also come in the this kind of question should also come for the context of secluded dark matter,
Okay.
because in secluded dark matter this annihilation of dark matter to dark photon is still there in the current temperature at zero temperature. So, but if the dark matter mass is heavy, then I think the constraints will be much weaker. The indirect detection constraints will be much weaker.
But in this case, you shouldn't have an enhancement. Um, in the limit when the mediator is much weaker, much lighter than the dark matter mass, you should have Sommerfeld.
Commercial enhancement.
Yeah. When it's you have a very heavy dark matter. But okay, this is another regime. Okay, so please go ahead.
Yeah, that's a separate context.
Yeah.
Okay, so let's move on. So let's discuss why we talk about muon colliders these days so much. So there are some advantages of going to muon colliders. So the main advantage is that we can have high energy as well as high luminosity. So this is because of the reduced synchrotron radiation compared to the electron colliders, because muons are like 200 times heavier than electron. So in the standard ring, we can produce large energy. At the same time, since muon is an elementary particle compared to the hadrons, so we can have an few TeVs of muon collider is as good as like the 100 TeV 100 TeV hadron colliders. And also it has got much less background compared to the hadron colliders. But it also comes with some disadvantages. Like the main few disadvantages are that muons are unstable with a lifetime of only 2 microseconds. And it is very difficult to produce collimated or low emittance muon beams. And muon induced backgrounds are always there in the forward direction because muon decays into the electrons and neutrinos. So anyways, people are working and the R&D group is working to produce low emittance or collimated beams. And also tungsten nozzles are proposed to put along the forward direction so that the beam induced background can be reduced. So anyway, so muon collider is still at the conceptual stage. So if it is realized, it is possible only after 2040. Okay, so my talk, the focus of my talk is primarily on TeV scale heavy dark Z. So for a heavy dark Z above 1 TeV, the current constraints are very weak. And the existing studies have focused only on the PP collider via the Drelian process. where this is the final, this is the process where the dark Z, once produced through the Drillian process, decays into the leptonic mode. So at the HL-LHC, which is supposed to work at 14 TeV, the projected sensitivity reaches up to 10 to the power minus 2 for epsilon and 10 to the power minus 1 for dark Z mass 1 TeV and 2.5 TeV. And proposed 100 TeV collider, FCCHH, can improve this sensitivity. I mean, it can, for the same masses, the epsilon can go to 4 times 10 to the power minus 3 and 3 times 10 to the power minus 2. So at muon collider, we can have 2 going to 2 or like 2 going to 3 annihilation channels. So these are some of the annihilation channels which I have looked into. So the first one is the dark Z production in association with photon. Second one is the dark Z production along with neutrinos. And the third one is the dark Z production along with muons. So to trigger events, we require a minimal cut like the photon and the muons to be like at least 10 GeV, and the eta, the pseudo rapidity should be within 2.5.
I'm sorry, but how is ZD decaying here? Is it invisible decay?
No. For our work, we have considered the scenario where the dark Z decays into the visible part sector. So all the dark matter candidates are heavier than the dark Z. I mean, the dark Z is the lightest within the hidden sector, and it can decay only to the visible sector through that kinetic mixing parameter.
Where is the missing PT coming from? If you don't have neutrinos
Missing PT can come in the second
in the
channel.
neutrin,
Yeah,
in the second channel only. Okay.
yeah. And to trigger events, I mean, to know that there is some missing energy, you need to have some observed missing energy.
But this is only for channel 2. In the other ones,
This missing energy is only for the channel 2.
yeah.
For the PT cut, the minimal PT cut of 10 GeV is for the other two.
Okay.
And for the, yeah, and all the observed objects should be in the central region of the detector. I mean, the pseudo rapidity should be within 2.5 to reduce the effects of the beam-induced backgrounds.
So you have to be far away from the direction of the beam.
Yeah, far away from the beam. If you try to observe events, observe objects which are close to the beam, it can get contaminated with the beam-induced background. The beam-induced backgrounds are along the beam direction, so we have to find objects away from the beam. So that's why we require this criteria.
Okay.
Okay. So these are the annihilation cross sections for all the 3 modes. I have shown the cross sections for the 3 TeV muon collider and the 10 TeV collider. So, and the cross sections are normalized with respect to epsilon square. So the key characteristics of all this process is that as the dark Z mass approaches the center of mass energy, the cross section increases. So this basically like the 2 going to 2 or the 2 going to 3 processes behaves like the 2 going to 1 process. So that's why the cross section increases for large dark Z. And also among the 3 annihilation processes, we can see that the 2 going to 2 process, which is dark Z along with the dark photon, this process dominates. Okay, now let's go to the decay modes. So as I said, the dark Z being the lightest within the hidden sector, so dark Z decays dominantly into the standard model or the visible sector. So the 2 primary decay modes which I have considered are the inclusive dijet and other is the electron mode. The inclusive dijet decay mode combines the multiple hadronic final states like the QQ bar. QQ bar also includes the BB bar mode and the TT bar, Tau Tau bar, and WW modes. So this TT bar can decay further into the hadronic mode, and this Tau lepton can decay into the hadronic mode, and Ws can also decay into the hadrons. So that's why I say that the inclusive mode. So the inclusiveness is shown by this letter X. So two jets. So dark Z is decaying into two jets plus anything else. Whereas the electron mode provides a very clean channel compared to the to the muon channel and any other channel. So that's why, along with the hadronic channel, inclusive digest channel, I have also considered the electron decaying mode. So two decay modes are considered. So based on these two decay modes, I can categorize the signal into two channels. This is the inclusive digest mode, and the second one is the electron mode. And over here, you can see the branching ratios of dark Z. The QQ bar decay is the dominant one. Okay, so let's go to the concept of photon recoil mass. So for a process like this, we can define the recoil mass of the photon like this one, where P1 and P2 are the 4 momentum of the muons, and P gamma is the 4 momentum of photon. And from the conservation of 4 momentum, we can see that this recoil mass is nothing but the mass of the dark Z. So the dark Z, so the mass of the dark Z can be estimated from the recoil mass, and it is independent. And this way of estimation of the dark Z mass is independent of the dark Z's decay modes. So at the detector, at the detector, the photon recoil mass and the electron-positron invariant mass distributions depends highly on the energy resolutions of the photon and the electron and positron. So this is the typical energy resolution expressed in this way, where these parameters A, B, and C are dependent on the pseudo rapidity, and E is the energy of the photon or the electron or positron, and delta E is the energy resolution in the detector. So when in the 222 process, when the dark Z mass approaches close to the center of mass energy of the muon collider, then the photon, it becomes less energetic. The energy of the photon goes to zero. As a result, the M recoil, the recoil mass distribution becomes very sharp. Whereas when the dark Z mass is much smaller than the center of mass energy of the muon collider, then the photon can be energetic, and that can make the distribution of recoil mass very broad. For the electronic decay modes of the dark Z, the opposite thing happens. This is because when the Z boson becomes heavier, the electrons coming from the decay of the dark Z becomes have higher energy, and as a result, the invariant mass distribution becomes broad. Whereas when the dark Z is lighter, the decays of the electrons coming from the dark Z have less energy, and that's why the distribution, the invariant mass distribution becomes sharper. So this I have demonstrated in this figure. So the photon recoil distribution is shown in the uh, blue distribution, and the electron positron invariant mass distribution is shown through this orange distributions. So as you can see, when the dark Z mass approaches to the center of mass energy of the muon collider, the recoil mass distribution becomes very sharp, whereas the opposite thing happens for the invariant mass of the electron positron. Is there any question till now?
Which kind of luminosity did you assume here? I mean,
For the 3 TeV, we are considering a luminosity of 1 inverse attobarn. And for the 10 TeV, the luminosity can be higher for muon collider, and it can go up to like 10 inverse attobarn.
Mm.
Okay, so this recoil mass and the electron-positron invariant mass distributions can then be fitted with a Gaussian distribution, and we can find the width. I mean, this widths basically. So these widths are nothing but the standard deviations of the Gaussian fits. So in this plot, we have shown the width for the recoil mass at 10 TeV, 6 TeV, and 3 TeV muon collider, and the width for the electron-positron invariant mass. So we can see for the recoil mass, the uh, the width actually decreases with dark Z mass, and when it is close to the center of mass energy, the width actually becomes very, very small. Whereas the opposite thing happens for the electron positron invariant mass. In this case, for the electron positron invariant mass, the width increases with the mass of dark Z. Also, one thing to note is that the the intersection of this recoil mass and the invariant mass happens just around half of the center of mass energy. By the way, we always have to keep in mind that the recoil mass, obtaining the dark Z mass from the recoil mass distribution of the photon, is independent of the decay products of dark Z. So this distribution, even though obtained for the EE gamma mode, the same distribution will hold for the inclusive digit mode. Okay, so let's discuss the time and that. Okay, let's discuss the signal and the background. So as I said, all the scattering processes should be limited to the central region, which is given by the zero rapidity should be within 2.5. The photon PT should be greater than 20 GeV. And since the dark Z is decaying into either jets or into electrons, so the leading jet and the leading electron should have high PT. So at the detector level, we demand a high PT cut of 10 GeV for the leading jets and leading electron. Whereas to enhance the number of signals, we have not put any strong cuts on the subleading jet or the subleading electron. Only 20 GeV is required for the transverse momentum. Okay, so how do we categorize these two signals? So for the inclusive dijet signal, we require that we should have at least two jets and at least one photon, and we should not have any electrons or muon with PT greater than 20 GeV, just a lepton veto. And similarly, for the EE gamma mode, we require at least two electrons and at least one photon, and the number of jets should be 0 for PT greater than 20 GeV. So after these two basic selections, we can have two mass window cuts, selection cuts. One is the recoil mass cut, which is given like this, and another one is the electron-positron invariant mass cuts. So these two cuts are the most important selection cuts because they can reduce the background by a significant amount. For the inclusive dijet, we have the dominant background is the JJ gamma, and the E gamma mode, this is the dominant background. So over here in this figure, we have shown the recoil mass distribution for background and the signal in the JJ gamma mode, inclusive dijet mode for the 3 TeV muon collider. So as we see, as the mass of the dark Z increases, the recoil mass also becomes sharper. So if we impose this recoil mass selection criteria, we can reduce this background significantly because the background distribution, as we can see, is very broad. Similarly, if for the EE gamma mode, I have shown the distribution for the electron-positron invariant mass. So as the dark Z mass increases, the width becomes larger, as I explained before. And this invariant mask card, selection card, actually reduces the background significantly because the background distribution is very broad. Any question?
A little bit confused. So in these plots, the histograms are the background, and
These are all histograms. So these histograms, the colored histograms, are basically the stacked background distribution. And these are
and
the
then
background.
and then you have the signal is represented by this
Red one, yes,
red ones.
exactly.
So
Yeah,
the signal is completely overwhelmed by the background. For instance, at 1 TeV for NZ
yes,
equal to 1 TeV.
yeah.
Even if I use a cut on a memory coil
Mhm.
around NZ, how do you distinguish this against the background?
And because the background distribution is very broad. So if you take events only over, I mean only this small region, then
Uh-huh.
the backgrounds surviving after this cut will be very small.
Because it's flat.
Yeah, because the background distribution is completely flat, very broad, and the signal distribution is very sharp. So if you apply this selection criteria, there will be no signal loss.
No, I don't understand. I don't understand because the events, the background event have the same value of memory coil of the signal. So how do you distinguish? So sorry, I don't see it, but probably it's trivial.
No, I
So
am also not getting your question. What did you say?
yeah, so I mean this the normalization of the two histograms. Okay, it will be for a specific, of course, it will be
Yeah,
for a
I mean it is
section.
actually it belongs to a particular choice of epsilon. So now
Yeah.
if I change the epsilon, so
Uh,
for example, if this signal is obtained with an epsilon of 0.01.
uh,
Now if I increase the epsilon, then the
yes.
signal cross section will naturally increase.
Yeah, yeah,
This
I
is
know,
just a
but
benchmark point.
yeah, so my point is if epsilon is 0.01, how do
Mhm.
you distinguish the signal from the background, even if you cut M recoil around 1?
In that case, for this particular choice of epsilon, for example, let's consider this one. Okay,
Uh,
so for this choice of epsilon, I cannot get any significance around even close to 2 sigma. But if I increase the epsilon
yeah, of course. Yeah. My question was that. So you need you are sensitive to larger value of epsilon, not
yes,
value of
yes.
epsilon issue there. Okay,
Yeah.
okay.
A similar thing for here also.
Mhm,
Okay.
mhm,
So this is the thing which I need to show to explain your question. So over here, you see the epsilon which we consider is 0.01,
mhm.
but 0.01 we cannot achieve the 2 sigma
Okay.
significance.
Okay.
So we need higher epsilon, where
Mhm.
the cross section scales as epsilon square. Signal cross section will scale as epsilon square. So this is the 2 sigma contour for the detecting dark Z through the process through the inclusive digest process shown in the left figure, and in the right figure we have the E gamma mode. So for the inclusive digest channel, we can only use the photon recoil mass criteria. So these 2 sigma contours are obtained once we apply the photon recoil selection cut. But for the case of the E gamma mode, we can impose the recoil mask cut as well as the electron positron invariant mask cut. So now the question naturally comes that which one we should use. We can use the recoil cut or the invariant mask cut, or we can also combine both of them. I mean, apply both the selection criteria. But
But for
applying
instance, do you have an estimation of the acceptance of these cuts?
In the main slide, I have not shown, but I have in the backup slides.
Order of magnitude, so 10%.
And this is for the, this is the recoil cut. Okay. I mean, this is after applying the recoil cut, but I do not have the. You want to see the how much the improvement is after applying these two cuts,
Yeah,
right?
yeah, of course. You apply a cut
Yeah.
because you want to improve. So.
Yeah, of course. But unfortunately, I didn't keep it in the slide to make it very simple. So
I see.
after the talk, I will get back to you. I will show the paper which I have written.
Okay. No problem.
Okay. So for the electron mode, as I was saying, we can apply the invariant mask cut as well as the recoil mask cut, both of them or either of them. So which one to use? So we have noticed that if we use the recoil mask cut for the heavier dark Z, then we have then the results are better, as you can see. These are the 2 sigma contours. The solid lines are the 2 sigma contours while applying the recoil mask cut. And the dashed lines are the 2 sigma contours if we apply the electron positron invariant mask cut. So the electron positron invariant mask cut is efficient for lighter dark Z, and for the heavier dark Z, the recoil mask cut is more efficient. And statistical significance are computed for each channel through this standard formula. And these two channels are combined using this statistical significance formula. Okay, so this is the final result. We have shown the 2 sigma the solid lines and the 5 sigma the dashed lines contours for the detecting dark Z after combining the inclusive dijet and the E gamma mode. So we can see that from the previous figure that the E gamma channel actually outperforms the dijet channel when the dark Z is lighter. But for heavier dark Z, the the inclusive dijet mode outperforms the E gamma mode. So if we combine those two modes, the improvement is not too high, but like a modest improvement within less than 10%. But yeah, this is the best sensitivity we can reach for muon collider. And for completeness, we have also shown the 2 sigma contours for the HLLHC and FCCHH. So we can see that for dark Z heavier than like 2 TeV, the muon collider outperforms the hadron colliders. Okay, so this is my conclusion. I have given an overview of dark Z, the current constraints from experiments, and the future sensitivities on the dark Z mass versus kinetic mixing parameter space. I had a brief discussion on the advantages and disadvantages of muon colliders, and I have discussed the searches for the dark Z at muon collider via the annihilation channel, mu plus mu minus going to dark Z and photon. And we have shown that by optimizing the photon recoil mass criteria and the electron positron invariant mass cuts, we can achieve the best sensitivity in muon colliders. Okay, so that's it.